NENOMATICA, where mathematics meets YouTube excellence. In this example, we will solve a radical equation by introducing an auxiliary variable. First, read the problem. Step 1. Substitution analysis. Notice that 1 over x is the square of 1 over the square root of x. We will set y equal to 1 over the square root of x. Then we will rewrite the entire equation in terms of y. Step 2. Form the quadratic equation. Substituting y equals 1 over root x into the expression, the equation becomes y squared minus 11, y plus 18 equals 0. Step 3. Factor the quadratic. We need two numbers whose product is 18 and sum is negative 11. Those are negative 2 and negative 9. So the factorization is left parenthesis, y minus 2 right parenthesis times left parenthesis, y minus 9 right parenthesis equals 0. Step 4. Solve for x. If y equals 2, then 1 over root x equals 2. That means root x equals 1 over 2, so x equals 1 over 4. If y equals 9, then 1 over root x equals 9. That means root x equals 1 over 9, so x equals 1 over 81. Important domain note: because there is a square root of x in the denominator, x must be strictly positive. Both solutions we found, 1/4 and 1 over 81, are positive and valid. Quick check. 4x equals 1/4. 1 over x minus 11 over root x plus 18 becomes 4 minus 22 plus 18, which is 0. 4x equals 1 over 81. 1 over x minus 11 over root x plus 18 becomes 81 minus 99 plus 18, which is 0. Therefore, the solutions are x equals 1/4 and x equals 1 over 81. Recap. We recognized a pattern and introduced an auxiliary variable y equal to 1 over root x. This turned a radical equation into a simple quadratic. We factored, solved for y, back substituted, checked the domain, and verified both solutions. Keep practicing substitution techniques to simplify complex-looking equations. Example. We will solve the equation, open parenthesis x plus 1 close parenthesis to the fourth, minus 13 times open parenthesis x plus 1 close parenthesis squared, plus 36 equals 0. We will use substitution to reduce it to a quadratic in a new variable. Notice the repeated pattern, open parenthesis x plus 1 close parenthesis squared. Let's substitute y equals open parenthesis x plus 1 close parenthesis squared. Then the equation becomes y squared minus 13, y plus 36 equals 0. We'll factor that. We look for two numbers that multiply to 36 and add to negative 13. Those are negative 4 and negative 9. So we factor as open parenthesis y minus 4 close parenthesis times open parenthesis y minus 9 close parenthesis equals 0. Thus y equals 4, or y equals 9. Now use the first value, y equals 4. That means open parenthesis x plus 1 close parenthesis squared equals 4. Taking square roots, x plus 1 equals plus or minus 2. So we get two solutions, x equals 1 or x equals negative 3. Now use the second value, y equals 9. That means open parenthesis x plus 1 close parenthesis squared equals 9. Taking square roots, x plus 1 equals plus or minus 3. So the remaining solutions are x equals 2 or x equals negative 4. Collecting all four solutions, we have x equals 1, negative 3, 2, and negative 4. We solve the quartic by substituting y equals open parenthesis x plus 1 close parenthesis squared, factoring a simple quadratic, and then taking square roots. Example. Solve the equation open parenthesis x plus 1 close parenthesis to the 6th power plus 20 equals 9 times open parenthesis x plus 1 close parenthesis cubed, using a helper variable substitution. Notice that the expression open parenthesis x plus 1 close parenthesis cubed repeats. We can set a helper variable. Let y equal open parenthesis x plus 1 close parenthesis cubed. This turns the 6th power into y squared. Now substitute. The equation becomes y squared plus 20 equals 9y. Move everything to one side to get the standard quadratic form. Y squared minus 9, y plus 20 equals 0. Factor the trinomial. two numbers that multiply to 20 and add to -9 are -4 and -5. So y minus 4 times y minus 5 equals 0, which gives y equals 4, or y equals 5. Back substitute using y equals open parenthesis x plus 1 close parenthesis cubed. For y equal 4, open parenthesis x plus 1 close parenthesis cubed equals 4. Taking the real cube root, x plus 1 equals the cube root of 4, so x equals the cube root of 4 minus 1. For y equal 5, open parenthesis x plus 1 close parenthesis cubed equals 5. Then x plus 1 equals the cube root of 5, so x equals the cube root of 5 minus 1. So the solutions are x equals the cube root of 4 minus 1, and x equals the cube root of 5 minus 1. Both come from the single substitution y equals open parenthesis x plus 1 close parenthesis cubed that turned a 6th-degree expression into a simple quadratic. We display the example and the original equation. Step 1. Simplify the products. We expand the binomial product using the FOIL pattern. The product of x minus 1 and x minus 3 equals x squared minus 4x plus 3. Now, we rewrite the original equation using this result. Step 2. Align terms to reveal the repeating expression. Notice that x squared minus 4x plus 3 equals x squared minus 4x plus 5 minus 2. Distributing the negative sign gives the transformed equation. Step 3. Substitute an auxiliary variable. Let y equal x squared minus 4x plus 5. Substituting y into the equation yields y squared minus y plus 2 equals 4. Move all terms to one side to get y squared minus y minus 2 equals 0. Factor to obtain y minus 2 times y plus 1 equals 0. Therefore, y equals -1 or y equals 2. Step 4. Solve for x using each value of y. Case 1. If y equals -1, then x squared minus 4x plus 5 equals -1. So x squared minus 4x plus 6 equals 0. The discriminant is -8, which is less than 0, so there are no real solutions for this branch. Case 2. If y equals 2, then x squared minus 4x plus 5 equals 2, so x squared minus 4x plus 3 equals 0. Factor to get x minus 1 times x minus 3 equals 0, giving x equals 1, or x equals 3. Quick challenge. Which step made the problem much simpler? The key was to spot the repeated expression and replace it with a single variable. Final answer x equals 1 and x equals 3. Recap. 1. Simplify any obvious products. 2. Align terms to reveal a repeated pattern. 3. Substitute an auxiliary variable. 4. Solve the simpler equation and back substitute. Example. We will solve the equation by using a helper variable substitution to simplify the algebra. Step 1. Substitution. Because the expression x squared minus 1 squared repeats, we define a new helper variable y equal to x squared minus 1 quantity squared. Then rewrite the original equation entirely in terms of y. This becomes y squared plus y minus 2 equals 0, which is a simple quadratic. Step 2. Factoring. Factor the quadratic in y. We get left parenthesis, y minus 1 right parenthesis times left parenthesis, y plus 2 right parenthesis equals 0. So the solutions for y are y equals 1 or y equals -2. Step 3. Handle the first case y equals 1. We apply the square root property. If left parenthesis x squared minus 1 right parenthesis squared equals 1, then x squared minus 1 equals plus or minus 1. That gives two branches x squared equals 2, which yields x equals plus or minus square root of 2, or x squared equals 0, which yields x equals 0. Step 4. Check the second case y equals -2. Because y equals left parenthesis x squared minus 1 right parenthesis squared, it must be non-negative. So the equation left parenthesis x squared minus 1 right parenthesis squared equals -2 has no real solution. Therefore, the real solutions for x are plus or minus square root of 2 and 0. In this example, we will find the sum of all roots of the equation 1 over x squared plus 1 over quantity 1 minus x squared equals 160 over 9. We will proceed in 6 clear steps that mirror the worked solution, combine fractions, expand and simplify, substitute t equals x minus x squared, form a quadratic in t, solve for t, then get the sums of roots for x from each t and add them. Let's start by showing the problem on screen. Step 1. Combine the fractions using a common denominator. The common denominator is x squared times quantity 1 minus x squared. We write the left side as quantity 1 minus x squared plus x squared over x squared times quantity 1 minus x squared equals 160 over 9. Step 2. Expand and simplify. Expanding 1 minus x squared gives 1 minus 2x plus x squared, so the numerator becomes 1 minus 2x plus 2x squared. For the denominator, notice that x squared times quantity 1 minus x squared equals quantity x minus x squared squared. Step 3. Substitution. Let t equal x minus x squared. Then the numerator 1 minus 2x plus 2x squared can be rewritten as 1 minus 2 times quantity x minus x squared. So the equation becomes 1 minus 2t over t squared equals 160 over 9. Step 4. Form a quadratic in t. Cross-multiplying gives 9 times quantity 1 minus 2t equals 160t squared. Move all terms to one side to get 160t squared plus 18t minus 9 equals 0. Step 5. Solve the quadratic for t using the quadratic formula. T equals negative 18 plus or minus the square root of 18 squared minus 4 times 160 times negative 9, all over 2 times 160. That becomes negative 18 plus or minus the square root of 6084 over 320. The square root of 6084 is 78, so t equals negative 18 plus or minus 78 over 320. Hence t1 equals 3/16, and t2 equals negative 3/10. Step 6. Get x from each value of t and find the sum of the roots via Vieta's formula. For t1 equals 3/16, x minus x squared equals 3/16, which gives 16x squared minus 16x plus 3 equals 0. So the sum of its roots is 1. For t2 equals negative 3/10, x minus x squared equals negative 3/10, which gives 10x squared minus 10x minus 3 equals 0. So the sum of its roots is also 1. Therefore, the total sum of all roots is 1 plus 1, which equals 2. We followed the exact structure, combined fractions, simplified, substituted t equals x minus x squared, formed and solved the quadratic in t, and used Vieta to add the sums of roots from the two resulting quadratics in x. The final sum of the roots of the original equation is 2. We are going to solve a satisfying algebra puzzle. We are given a quadratic that involves a cube root, and our goal is to evaluate a larger expression named a. We'll proceed step by step, and I will pause for quick challenges along the way. First, let's place the problem on screen. Step 1. We start from the quadratic x squared minus the cube root of 2023 times x plus 4 equals 0. Because the constant term is 4, we can confirm x is not 0. That allows us to safely divide the entire equation by x. Let's divide each term by x. Now collect terms to isolate the useful sum x plus 4 over x equals the cube root of 2023. Quick challenge. Look at the definition of the big A expression. Where do you see the pattern x plus 4 over x minus 2? Great. We'll turn that into a single symbol to make everything cleaner. Step 2. We will create a substitution. Let t equal x plus 4 over x minus 2. Since we have x plus 4 over x equals the cube root of 2023, t becomes that cube root minus 2. Now rewrite the big A in terms of t only. That gives t cubed plus 6t squared plus 12t plus 9. Step 3. Recognize the binomial cube pattern. The expansion of open parenthesis t plus 2 close parenthesis cubed is t cubed plus 6t squared plus 12t plus 8. Notice our A matches that pattern, but with a 9 instead of 8. Split 9 as 8 plus 1. And then we can rewrite A as open parenthesis t plus 2 close parenthesis cubed plus 1. Step 4. Substitute t equals the cube root of 2023 minus 2 back into A. Then t plus 2 becomes exactly the cube root of 2023. Cube that to get 2023 and add 1. Therefore, A equals 2024. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.